Hi everybody, Mrs. White here. Today we'll be taking a look at something called trigonometric ratios, which will become three powerful tools that can help us find missing sides and angles of right triangles. To get our brains ready for today's lesson, I wanted to take a quick look at these two warm-up problems with you. You'll notice in the first problem, part A, that we know two sides of the triangle and we want to find the third side. We already have worked with a powerful tool that helps us do this, called the Pythagorean theorem. Noticing that the side across from the right angle is 17, that's the hypotenuse, that will be our C, we can set up the formula a squared plus b squared equals c squared, in this case 15 squared plus x squared equals 17 squared. And then we can do the algebra, squaring both sides, squaring the numbers, subtracting the 225, and undoing the square with a square root, to learn that the missing side had a length of 8. If we take a look at this second problem, we actually cannot use the Pythagorean theorem because this triangle does not have a right angle. The Pythagorean theorem is only a tool that can be used for right triangles. When we look at this third example, we're back to having a right angle, but unfortunately we only know one of the sides, which leaves us with not enough information to find this x value right here. It turns out we would either need to know the third side so that we could use the Pythagorean theorem, or if we knew an angle, we'll be able to use the powerful new tools that we'll take a look at today: sine, cosine, and tangent. I also wanted to take just a minute to review a couple basic algebra moves that are useful when we're trying to isolate the x, when we're trying to solve an algebraic equation. In this first problem here, you'll notice that x is being divided by 5. So we can simply multiply both sides of the equation by 5 to undo the division. The 5's cancel, and now we know that x is 40. The second equation is going to involve one extra step because the x is in the denominator. We can start off the same way. 12 is currently being divided by x, so if we multiply both sides by x, we undo the division, leaving us with 12, and on the right side we now have 2 times x, or 2x. The only glitch is the x is not fully isolated. It's still over on the right side with that 2. So now we can use division, divide by 2, to get to our final answer, x equals 6. So one extra step when the x is in the denominator. We need multiplication to undo the division, but then we end up with multiplication that still has to be undone. We'll be using those solving moves today as we solve for missing sides and angles of right triangles. Okay, let's take a look at our three main trig ratios: sine, cosine, and tangent. These are algebraic functions that have an input and an output like any other function. The difference here is that when we're dealing with sine, cosine, and tangent, the input is going to be an angle. So for example, if this angle was 50 degrees, we would do sine of 50. The input is always an angle, and the output is always this ratio of sides. Those of you that have worked with this in the past, we have this acronym, SOH, TOA, that helps us remember these trig ratios. So the S, the C, and the T stand for sine, cosine, and tangent. The O, the H, and the A mean opposite, hypotenuse, and adjacent. So let's take a look over here first at this triangle to get a sense of what we mean when we say opposite, adjacent, and hypotenuse. When we talk about opposite, adjacent, and hypotenuse, we always need some angle that we're referencing. And in this case, I highlighted angle A. So if angle A is my point of reference, then we can see that side A is across the triangle from that angle. And that's when we use the word opposite. Opposite as in across. Adjacent means next to, and you might wonder, well, aren't these both next to angle A? Well, they really are, but the hypotenuse we already know is always the longest side of the triangle. So by default, C here is the hypotenuse. It's across from the right angle, which then makes B be the only remaining side, which is therefore the adjacent. So opposite is across, hypotenuse is always across from the right angle, and adjacent is basically your leftover side that happens to be right next to your angle that you're referencing. So now the way these functions work, when I talk about sine, SOH tells me that sine is the ratio of opposite over hypotenuse. So when I'm using the sine function, I'll input an angle, and what it outputs is this constant ratio of sides, the length of the opposite side compared to the length of the hypotenuse. Now notice over here, if I'm using angle A as my reference point, that sine would be opposite over hypotenuse. That would give me A over C. But now if I move over here to angle B, now B is my opposite, C is still my hypotenuse, giving me sine of B equals B over C. Notice that the sides that you choose to use depend on the angle that you're using as your point of reference. Okay, you might be wondering, well, don't we have to know how big the triangle is if we're going to talk about this ratio of sides? So let me open this tool here. Okay. It actually turns out, if you think back to our explorations in the past about similar triangles, that one of the special traits that similar triangles have is that the ratio of sides is constant no matter how big or small the triangle. So for example, if I take this 30-degree angle, this triangle here that has a 30-degree angle, I can enlarge it and I can shrink it all I want. And look at those ratios over on the right-hand side of the page. They're not changing. It doesn't matter if the triangle is very small or if the triangle is very large. The ratio of opposite over hypotenuse will stay 0.5 as long as that angle that we're referencing is 30 degrees. And it actually turns out this is our sine ratio right here, opposite over hypotenuse, cosine, adjacent over hypotenuse, and tangent, opposite over adjacent. These ratios are constant as long as I am referencing the same angle. If I make the angle bigger, now these ratios change, but I can still shrink and dilate that triangle, and they're constant for that 41-degree angle. So as we move forward, if I take the sine of 41, my calculator should give me 0.656. That's that constant opposite over hypotenuse ratio for any 41-degree angle. Let me get back to the page with our problems here. So let's take a look now at how we can use these ratios to help us solve problems. One suggestion I would make in moving forward here is that before you attempt to write any math on your piece of paper, that you really get squared away in your head which of the three ratios, sine, cosine, or tangent, will be most useful to you in solving the problem at hand. So when I look at problem number 1 right here, I see this 32-degree angle. And if I look at the location of the sides, I do not know the opposite this side this time, but I do know the hypotenuse, and I do know the side next to the 32, which we'll call adjacent. So I've got adjacent, hypotenuse. So now I might say to myself, adjacent over hypotenuse, that's my CAH, which is my cue to use cosine in this problem. So as I go to set up the equation, I'm going to take cosine of the 32-degree angle, and what that gives me is the ratio of the adjacent to the hypotenuse. So the adjacent is x, the hypotenuse is 18. I now know that x over 18 should equal whatever my calculator tells me cosine of 32 is. Now I have a little algebra equation I can solve. X is currently being divided by 18, so if I multiply both sides by 18 to undo the division, I can now go to my calculator and type 18 times the cosine of 32, and I should see 15.26, which is therefore the length of this side that we were trying to find. Let's take a look at a couple more. The second example right here, if I look at my 51-degree angle, I see that the 10 is across or opposite from the 51, and that the x is not the hypotenuse and is therefore the adjacent. So now I'm going to say to myself, I've got the opposite and the adjacent, that's TOA, that's my cue to use tangent in this problem. So as always, I'll take tangent of the angle, tan 51, and set it equal to that ratio of sides, opposite over adjacent, which in this case would be 10 over x. And this is like that second warm-up problem now where I have a little extra work to do because the x is in the denominator. But I can still start off by using multiplication to undo the division. The x's cancel out. I now have a 10 over here. Notice my x ends up being multiplied over here on the left by tangent of 51. That's no problem though. I can undo multiplication with division. So if I now just divide both sides by the tangent of 51, I can go to my calculator and type 10 divided by tan 51, and I should get the correct answer, 8.10. Let's look at one last one, just so we can see how sine looks. Sine is the problem where we are dealing with the opposite and the hypotenuse. And so that's my SO, which would be my cue to use sine. So just like in the other two problems, I'm going to take sine of the angle, sine of 42, set that equal to the appropriate ratio, which in this case is the opposite over the hypotenuse. And once again, I end up with one of these two-step solving problems where the x is in the denominator. So I'll multiply both sides by x to undo the division, and now the x is not fully isolated, so we can use division to undo the multiplication. Go type 200 divided by sine of 42 in your calculator, and we get the correct answer, 298.90. So here's your just basic intro into using sine, cosine, and tangent as functions that provide these ratios that apply to these similar triangles. So you might be wondering, well, what if the problem is not so easy to look at, where I've got this angle sitting on the ground and it's so obvious where the opposite, the hypotenuse, and the adjacent are located? What if we rotate the triangle? So now this right angle's up in the air, everything seems to be in different places. The question is, how does that change the problem? Well, it turns out it doesn't. It's the exact same triangle. All we did was rotate it. If you had a piece of paper, you could rotate it right back. But let's take a look at how we can figure this out without having to turn our paper. I'm going to start off by finding the angle, and I'm going to make it my first job to figure out if the sides that I'm looking at are opposite, adjacent, or hypotenuse. Just like in the original orientation, I do not know the opposite. What I do know is the hypotenuse across from the right angle, and then the side right next to the angle, which is adjacent. So the 18 is still the hypotenuse, the x is still the adjacent, which is my CAH, meaning I would still use cosine, and essentially I would go do the exact same work I had already done up above. The triangle was simply rotated sideways. When you access the notes version of this, the PDF that I posted for you, you might want to try this problem right here, see if you can do it yourself. One last learning target for today. What if it's the angle we don't know? So let's take a look, going back to this problem we've already looked at a couple of times, where we have the 32 and the x and the 18. What if I change the location of the 32, the x, and the 18? So the x is now the angle, the 18 is now the adjacent, and the 32 is now the hypotenuse. The question here is, what changes, what stays the same? What doesn't change is that this is still a cosine problem. If I look at the orientation, the 32 is still the hypotenuse, the 18 is still the adjacent, and so that would still be a CAH or cosine problem. The difference comes into play when I go to set up the equation. We said that for trig functions, the input is always an angle, and the output is always a ratio of sides. So when I go to set up this problem, I'm going to still use cosine, but now my x is the angle. So I'm going to set up my equation as cosine of x and set that equal to adjacent over hypotenuse, which in this case becomes 18 over 32. But now I have a problem. I want to isolate this x, and there's a cosine in front of it. In other words, the angle has the cosine being taken of that angle. So I need a way to undo cosine. And I'm not going to use division because division is strictly for multiplication. What I need is actually an inverse function. So let's look over here about what we know about inverses. Original functions take us, in this case, from an angle to a ratio of sides. So the inverse should do the opposite. It should take us from a ratio of sides back to the angle, which is exactly what we want to do here. So when I look at my problem, cosine of x equals 18 over 32, the move I need to undo cosine is inverse cosine. That will reverse what cosine does. So I'm going to take inverse cosine of both sides. On the left side, inverse cosine just completely undoes cosine, leaving me with the x I'm trying to find. And on the right side, I can now go pick up my calculator and type inverse cosine of 18 over 32. You'll find that located right above the original cosine button on any calculator. And if I type in inverse cosine of 18 over 32, I end up with 55.77 degrees, and I now know how big this angle is. Another example is in the notes at the bottom for you. Thanks for listening. See you soon.